The screen is visible. So good evening and welcome to the week 12 of the live interaction session of the fundamentals of micro and nanofabrication. The course instructors are Professor Susovan Avasti and Professor Sankar Selvaraja from ISC Bangalore. I am the PMR of Teaching Assistant Vikas Pandey from IIT Jodhpur. This is a brief about me, the classroom link which we will be completing today anyway, the YouTube channel in which all these lectures will be uploaded, and my contact details in case you need to reach to me. So till now we have seen many processes starting from the basics of a silicon wafer or silicon or other semiconductor wafers, going to cleaning process and then oxidation, film deposition, lithography, etching, and all other processes. In the previous class, we saw a bit about process integration. We'll continue over it and we will take some case studies that has, like in a sense, we will be first summarizing some things that has been towards week, and then we will be discussing some related questions. Before starting, if you have any queries or any questions, you are free to ask, or we can even discuss at the end of class. Yes, any questions?
I have a question related to process integration, sir, but we will
Okay.
see. Maybe you may maybe cover that.
Okay.
Let's see.
Like from this week, some questions or the
This week only.
we will discuss at the end.
Yeah.
So let's start the class. So anyway, we have covered what is process integration. So process integration, uh, the goal is to combine individual unit processes. Till now, we know each process, but when taken as a unit, like each process is dependent on each other. Like they are either essence or they have to be like if we have to do litho, we want to know what option is there, and when depositing, like what process is to be done. All such things are interrelated. So when we are uh, combining these individual unit processes into a chain, it is relation, and that will result in our device. So uh, to do the process integration, we require detailed knowledge of various fabrication techniques and keen attention to details. It at the it ensures that high yield and device is repeatable, not that we are able to make some device only once and we are not able to repeat what happened like that. So if we have good process integration, in that case, with device repeatable good yield, whole process can be optimized. It is a multidisciplinary field. It means since we are dealing with chemistry, person who is doing this preparation should have knowledge of chemistry, physics, since basic physical processes are involved, as whole electronics, and this comes under physics, and material science and devices. So process integration technician or process integration engineer are very important to ensure the smooth execution of all the steps to create functional devices on the wafer. So, and along with this, there is something which is that is documentation and modularity. So each team of unit process engineer, device engineer, and circuit engineer works with specific layers of abstraction and completes primarily through documentation. That means we'll like specifications and this while transferring the device to the next process or to the device engineer. So this ensures that components like microchips with many are reliably created without the need of constant collaboration. Like again calling that up. What is in this? What kind of chip this is? And this is not required. With the chip itself, there is a proper detailed record or documentation that is sent. And this documentation is records that are repeatability, successful integration. If someone has that is also documented. And if the documentation is good, that will the process and can be replicated without mistakes. Because sometimes it may happen that although like although they are doing some modification process due to 5G, but they are not recording the changes. They are just taking what is the optimal process document, and they are just sending it along with the uh, whatever process they have done, and that can lead to this wrong documentation can actually lead to like the next processes or maybe the lab process. Proper document, proper and detailed document is essential. So now we will see some case studies which Sir has good, in which specific changes can lead to uh, like how to tackle some problem, how to resolve this. Like first one is a case study of state selection. Like what substrate we have to choose. We started in the first class itself that we talked about. Hello. Yes. Hello. Am I audible? Okay. So in one of the case study, we will see the choice of substrate. That is, we have seen about silicon, germanium, gallium arsenide, PET, and many other substrates. And this is having a critical impact on the electrical, optical, thermal, and mechanical properties. The considerations include thermal tolerance, mechanical strength, and surface finish, single or double side polish. Like in case you are going for some MEMS fabrication where you need to make structures on both the sides, then you will go for double side polish. But in general, when we are talking about most of the circuits we are making, we are generally dealing with single side polish. But when we need sometimes a back contact or something like that, in that case we will then need a double side poly. Like suppose someone needs to deposit germanium on titanium nitride. Someone deposits germanium on titanium nitride. That results in droplet formation due to poor surface fitting. The solution is since the surface tension and wetting properties uh, must be carefully considered when selecting this substrate. Like it could have been done on another substrate instead of titanium nitride, and then the problem would not have happened. Second is about material compatibility. Different material can have different addition, thermal expansion, and mechanical properties, which can lead to delamination, peeling, or patterning issues. Like when nickel is deposited on glass, it shows nickel on glass shows poor adhesion. And if it is poor adhesion, then it will come out, peel off, and get overdeveloped, and patterning is difficult. So, a thin adhesion layers like chromium or titanium can be used between nickel and glass to enhance adhesion. Like even in case of silicon, when we are depositing gold over it, specifically for sensors, we are putting chromium below it because gold cannot directly be like it can be deposited, but it will peel off easily. That's why we are putting titanium or chromium below it. So, what are the process effects on the device? Like thermal treatment or exposure to plasma and etching can have effect on device performance. Like in case of E-beam evaporation, X-ray is generated and that can damage silicon interfaces. Or if we say profile consideration, like etching profile, if profile roughness, that is example of we see that in case of deep RI, we are etching again and again. So such scalping is done. Okay, it is not a smooth surface. So in this case, uh, if the profile roughness is impacting the device performance, other etching techniques can be used, or some post processing like how to make it smoothened out, that we have to see, because if it is having some negative effect on our performance, or there can along with this there can be some thermal constraints. Like once we have done metal deposition, high temperature processing should be avoided. Like if you have already done deposited say aluminum, and then you are then trying to do oxidation of silicon, that will damage aluminum because the oxidation is being done at 1100 degrees Celsius. That will that will melt the material, uh, aluminum metal, and then we will not get good devices. Hello, am I audible?
Yes, sir.
Okay. Yeah. So next case is uh, formation of silicon dioxide. Uh, say if a student deposited a metal oxide on a highly doped silicon substrate. So metal oxide, we can say, let's say zinc oxide. Okay, this is a semiconducting in nature. So to do uh, this deposition was done at 900 degrees Celsius in presence of oxygen to understand that what will be the current flow or what will be the nature of this Jadano. But what happened is that a thin layer of silicon dioxide formed on the silicon since we are doing the process at 900 degrees Celsius. So on the top of silicon, we wanted to deposit Jadano, but at first we got, due to the heat and presence of oxygen, we got a thin layer of SiO2, and thus all the all the plan that that student might have got disturbed because now it is not conducting in nature. The electrodes, whatever he has made, that becomes insulating because below there is SiO2. So in this case, what he could have done is that could have used FTO, that is a fluorine doped tin oxide substrate. FTO is a glass like like it looks like glass, a substrate quite commonly used. So it is already oxide, but it is conductive. FTO is fluorine doped tin oxide, that is uh, oxide, but it is conductive. And even in this case, if it is oxidized further, there is having no effect. Okay, so we should always be aware of how much process steps or temperature, atmosphere, pressure can affect our device. So if this person already knew that till now whatever process has been done or whatever substrate I am having, that is able to work fine till this temperature. Say if we are going till say 550 degree, it will work fine. So either he would have selected the substrate properly or he would have uh, optimized his process below this temperature so that uh, he will not destroy the substrate. Then next is the knowledge of equipment capability and alignment issues. This is quite common for lithography. So before doing any process, we have to communicate with process specialist. That is like suppose I am thinking that such process I will do, and I am directly going to do that. But the person who knows about the process or who is a specialist or who operates those devices or those processes, we have to understand the limitations because theoretically it might be that we can have any amount, any size of wafer, any uh, any kind, any temperature in our theory. But practically, what is possible? Say in the process that we are talking about, the machine can go till say 300 degrees Celsius, but what process we were thinking about, that has to happen at 500 degrees Celsius, so not possible. Suppose that the lithography machine I have uh, in our lab that is able to handle 3-inch wafers, but we have already done all the processes on 4-inch wafer. Such things can such things has to be avoided, like a problem that a small sample, say 1 centimeter square, cannot be properly aligned on standard wafer board because if we see, I have not put here, if we see the chuck that is made, it have rings, such rings, okay, and it has 2 3 vacuum openings, okay, which will suck and keep the wafer. So it is designed such that it is for 2-inch wafer, 3-inch wafer, and 4-inch wafer. If you change the o-ring, it will just shift like that. But a 1 centimeter square size is much less than even a 2-inch wafer, that is standard. So In this case, what will happen is that since the vacuum checking is not working, uh, when it generally happens in our case also, since in research we are mostly dealing with smaller samples. So sometimes if this this size of very small size of wafer is used, everything is aligned perfectly before lithography, but when it comes near the mask due to for this proximity printing, proximity lithography, due to the reverse pressure of this vacuum chuck, it will misalign. It will just move from its position. So in such cases, customized design of mini boards has to be used so that such small wafers can be hold properly and any kind of misalignment is not there. So before starting the process, we have to plan for the equipment's physical constraint to prevent delay and failure in our processing. Next, very important part is mask design. We have covered some part of mask design in the previous class also. Like we saw about what are the critical areas and all this. Okay. So one most important part of mask design is its critical points. Like the mask must account for alignment marks, process variability, and test structures. It should not be like directly the things we want. Along with that, it must have alignment marks. While studying about lithography, we also talked about it. So, since lithography is one of the major part of this whole micro and nano fabrication, we must take care that there are proper alignment marks. And these alignment marks should be such that they account for the process variability. It should not be that it can tackle only one kind of process. Suppose that someone is dealing with, say, 3-inch wafer. Another person comes with a 4-inch wafer. So it should be such that it tackles 3-inch. The alignment marks are placed such that they can be tackled for 3-inch wafer as well as 4-inch wafers. And there should be some test structures like on the sides or somewhere, seeing which we know that our other parts must have been right, because each and every uh, structure cannot be inspected. So such test structures like we saw alignment marks were in one of the test structures. Then we have such bands which have different thickness, like thick, with different thickness and in the sides, which are used to to see whether this process was fine or not. What is the limitation we got? What is the critical thickness we are able to replicate in this process? Like a micro heater design shows consistent misalignment due to incorrect mask design for front and back etching. So a micro heater is such design that there is a wafer where on the top there is a structure and at the bottom there is a structure. Say we have to make a diaphragm kind of structure that has to align to the top. So uh, what happens is that many a times we when we are designing, we are just making a design and then another design, and we are overlapping with each other, and it looks fine since it is overlapping. But in this case, it might have happened that the person didn't account for understanding that this wafer that micro heater has been designed on the top is actually going to be flipped, since it is now in the back side. And if it is not now flipped, this alignment marks will shift, because left, right, some symmetry can be a problem. It might be not it might not be a mirror symmetry. So the solution is to design such masks so that they have mirror symmetry. It's not that on the left hand side you are having some different kind of structure, right hand side different kind of structure. If it is mirror symmetric, even after flipping the mask, flipping the wafer, you will get the same kind of symmetry. So poor mask design can cause serious device issues. So it has to be planned carefully. So when we are designing the mask, or when the mask goes for even for printing and all, that time the device has not been tested, not even a single time. So it is not, and it is not possible to design the mask, then make the device and then test. That is not the correct way. The correct way would be to take in account what issues can be there, what are the problems that we might have, and we account already in the mask for all those problems before sending it for printing, and then later on we check and we verify, and we will get, say, at least 95 to 97% accuracy, or whatever we wanted, we should get that. So next are, uh, how do we ensure reliability? One very important thing is that many a times whatever we think or whatever has been optimized, say there is a process that at, say, we are doing RF sputtering, we have learned about sputtering, right? And it is optimized that it gives 200 nanometer depositing at 60 watt for, say, 1 hour. Done. Okay. Now, if we do like that, if someone just goes to RF sputtering, put 60 watt for 1 hour and 200 nanometer, he is expecting, and then goes to the subsequent process, then further process. But what if this was not 200 nanometer, instead it was 250 nanometer? So when he will try to etch out this with the optimized value, that is, say, in 30 seconds it is going to etch out, it will not, because 50 nanometer will be left. So what sorry so what has happened is that he didn't do characterization at each step. So inline characterization, like after each step or in between, we have to do characterization. We have to check. Like for this, some dummy samples are used. If we have like a long process flow, one step after that, some step, like say we have to do 30 steps, or say even for simple, let's say 7 to 8 steps. So in such cases, we can have dummy samples. Say in the beginning, I have to make, say, 100 devices that will go through 20 steps. So along with this wafer, I can put 20 dummy samples for optimization of each of the steps. Even if some fails, 20 small dummy samples that will not be of the same size. Okay. Like when we are doing the deposition, along with that, we will put a small dummy sample, clean silicon wafer, say, and we can put a strip over it, or we can pattern, like we just put a cover or strip over it, sharp cover, and then we go for profiling and check the thickness. If it is giving the correct one, it's fine. If it is not, so we have to understand, okay, what is the problem? Either the whole process has to be repeated, or in the subsequent processes, that documentation is to be maintained, that this is the change, and accordingly we have to change the other processes. Like suppose if in some case where we have to make cantilever, silicon nitride of 100 nanometer was to be deposited, but actually 94 nanometer is deposited. This small difference can significantly impact the device performance based on tolerance. Like if the tolerance is of say 2 to 3%, then it is a problem. If the tolerance was say 10%, it is fine. So in some cases, in the device itself or the technique of deposition itself, characterization is possible. Like if some cases these crystal monitors are there, they help us properly understand. But there are many processes like CVD in which we can not have a characterization inbuilt. So after the process itself, we have to go for the characterization. So till here, we have covered this like process integration. Now we'll cover a bit about silicon solar cells. So any questions till here?
Nothing, sir. Whatever question I had, it's already covered. Thank you.
Okay, thank you. So let's see uh, about silicon solar cells. So these are solar cells are becoming too common nowadays, and they are also made using silicon. The technology is very much similar to microfabrication, but it is not that complex. Does not involve so much of technology like micro or nanofabrication, but that is still somewhat a, a peripheral field of microfabrication and nanofabrication. So we can say it comes under silicon semiconductor or semiconductor device. So the basic structure of a solar cell is a p-n junction, simple p-type and n-type junction, which is optimized for light absorption. So they are essentially diodes. So we have already seen this is the symbol. So in like in our general physics, we see p and n type like this. But in reality, like if we are talking about say silicon, so it is say p doped silicon, and then we have n doped silicon over it. So we have one electrode here and one electrode here. So in this part, we will have a p-n junction, that is a diode. So it is the basic structure is like the basic structure is like a p-n junction diode only. In case of designing efficient solar cells, the main goal is to reduce recombination losses to increase efficiency. At present, the efficiency is not good for solar cells. Like the general commercial ones have uh, in the range of 25 to 40. Like this is the that is the conversion rate. What if still we are like getting a lot of energy from solar cells? What if we could achieve say 90% or 95% efficiency for solar cells? So what are the key components? Um, like in the front, there are front side grid, that is thin metal fingers that will collect the current, which like it should not be. We when we see the solar plates, we see some shiny metal lines there. So they are very thin metal fingers that allows to collect the current that is generated from each cell. So it is not that the whole plate is the solar cell. There are multiple solar cells, almost like 2 to 3 centimeters square in size. So from that, the current is collected, as well as this structure should not obstruct the light. Then on the back side, we have highly doped P plus layer that will reduce recombination at the contact point. Then we have uh, some inverted pyramid kind of structures that allows to catch more light, that enhances absorption and reduces reflection. So in 1991, the first best recorded efficiency of solar cells was 25.4%, in which some additional layers were used. What it was is that it was having inverted pyramids created using anisotropic etching. We have already seen that using KOH or even TIMA, we can have a pyramid kind of structure where since KOH etches the 100 plane but stops at 111 plane. Okay, then these metal contacts were not laid throughout, but at a specific point to minimize the recombination while allowing the current extraction. Then silicon dioxide was used at the surface to minimize surface recombination as the passivation layer. The second advancement that was done in the solar cells in 1991 was the front side that was having an N plus layer. For N plus means highly doped N layers for better carrier collection. And in the back side, there was P and P plus layers to reduce recombination losses. So two things we have to take care. Whatever carrier is generated, we have to collect that, as well as we don't want the carrier to recombine and uh, get back into the system, since we want more electrons to be extracted. So the solution was on the front side using P layer and the back side of the wafer to have uh, in the front side N layer or N plus layer, and the back side P plus layer to reduce the recombination. So the challenge in this whole process is that the high efficiency solar cells involve multiple lithography steps and doping processes. So the structure is much simpler compared to a semiconductor chip, or we can say processors, but still it requires multiple lithography steps. Why? Because the structure is complex. Uh, the physical structure is complex, the pyramid kind of structure. Then we have to carefully uh, have point contacts, as well as to do this, we have to do multiple lithography and multiple doping, having different values like P, P plus, and N plus. So inverted pyramid, N and P doping layer, metal grids, and point contact. All these require precision. And that's why the cost and the number of process steps increases. So along with this, there is a thing that solar cells must be manufactured in high volumes and at low cost. So unlike semiconductor industries like Intel, AMD, solar cells just solar cells have a uh, like have a opposite behavior in the term that while in case of semiconductor fabrication, micro and nano fabrication, we are moving towards smaller dimensions, because there in lower dimensions we have advantage, because we want to use less and less power. But opposite is true for a solar cell, because larger the surface area, more will be the power generated. So uh, Here we want larger surface area, but we want the processes to be scaled down. That is, the contacts or other process contact should be very minute. This inverted pyramids, if they are small, they will increase the efficiency. But overall, we want a big surface area. So that also increases the uh, constraints like complexity of the code system. So in 2011, a, if we see the current trends, say, so the largest cost factor in case of solar cells is the silicon wafer that amounts to 40 to 50% of the total cost. Other significant costs are cell processing, module assembly, and balance of the system. These contribute to other significant costs. So, one of the key ways in which at present the cost of this silicon solar cells can be reduced is by minimizing the thickness of silicon wafers while maintaining the efficiency. So all the processes same, but have a very thin silicon wafer. So less silicon, the cost will come down. So the challenge at present is advances in the thin film technology, alternative crystal growth techniques, and using recycled silicon. So using these techniques, the silicon cost has been reduced. Like now we can deposit a thin film of silicon as well as epitaxy, if epitaxy growth has improved, and silicon that has been previously used, say, in some discarded solar cells or phones or other things, that can be reused to help reduce the silicon cost. So the industry roadmap is goal is to reduce silicon consumption while at the same time improving the cell efficiency. Till 2011, in the 2011, silicon wafers were the most expensive component. So the focus was to reduce the wafer thickness and improve the light trapping and passivation technique. So this industry roadmap 2011 focuses on uh, reducing the silicon thickness. What is the current trends? The In 2019, the solar industry achieved further cost reduction through innovations in heterojunction solar cells with even higher efficiency, say around 26%, as well as improved light management techniques and cheaper manufacturing process. And uh, one revolutionary thing that is going to revolutionize this solar cells technology in near future is perovskites. So a new material like perovskite for hybrid or tandem solar cells has been developed. So this is something that is not, I think, not yet in market, but a lot of research going on perovskites. Okay. Mm, okay. So one is having new materials, all these things. But along with that, whatever technology we already have, how that can be uh, improved. Because the best way to reduce the cost of this wafers, solar cells is reducing the silicon thickness. So what are the challenges? So initial goal was to reduce from 400 microns, that was the standard silicon wafer, to 150 microns. Thinner the wafer, it is easy to break and have lower yield. So, but now this due to the advancement in technologies, now we have 180 micron wafer thickness, because above like below 150 micron we are not able to sustain, that yield will lower. So the solution was that yield is like we have to understand that yield is more important than cost reduction. So what if we are doing something at a lower cost, but overall the cost will increase if the throughput is low, since the wafers will break easily, and that will lead to loss in other terms. That's why sometimes we have to have a balance between these. Even if like the 50, if they start using 50 micron thickness of wafers, it will give uh, better throughput, but at the same time, overall it will have a lower throughput, since lower yield, since it will break easily, and many of the devices will fail due to breakage. So yield is more important than cost reduction through thinning wafers. And loss of wafers due to breakage is more expensive than using slightly thicker wafers. So at present, 180 micron wafer thickness are used in case of solar cells. So what is the importance of throughput? Throughput is the number of wafers processed per unit time. Say in 1 day or 1 week, say how many wafers are processed. Okay. So unlike the CMOS manufacturing, in which we are talking about scaling down, it is not beneficial for solar cell. So to improve the throughput, it will be fast processing and high throughput. This is the goal, that is around 30 wafers per second. If that is achieved, that will give us a good throughput, very high throughput. So with traditional processes like photolithography, sputtering, it is uh, very difficult to achieve such kind of uh, you see such kind of speed, 30 wafers per second. To do a photolithography process itself, it can take at least it, even if everything is maintained, every alignment, everything is done, even for the exposure it will take 8 to 10 seconds. Okay, so the solution includes simplified process and faster processing time. One is having simple process, second is faster processing time, and easily be, this can only be achieved if it is being done in the batch. Like, although the process single process can take 8 to 10 seconds, but what if in the single process now there are 1,000 wafers that are being processed? So 8 seconds for 1,000 wafers is more like that will increase the throughput. So there are different nowadays there are different kind of solar cell structure, like the standard aluminum back surface field solar cell structure. So it is like a vanilla silicon solar cell structure. So it is having a p-type wafer of around 180 micron thickness. Since lower the thickness, better is the throughput, and the standard thickness for any wafer is like 350 to 400, but in case of solar cell we are using 180 micron thickness. So with a single n-type diffusion, so it is a n-type wafer. Now aluminum backside field, so instead of p plus layer, for cost efficiency, a aluminum backside surface field is used. Front side is texture using pyramids for better light trapping, and the contacts are screen printed for simplified metallization instead of going for this deposition using say thermal evaporation and then doing the lithography, screen printing is used. That reduces the cost further as well as the process complexity. So since there is no N plus layer, so there is no need for lithography on the back surface. So the texturing can be done using simple wet etching like KOH and NOH since they etch out, they have the property that they stop at 111 plane. So without lithography also, uh, texturing can be done. So what is the process of making this AL BSF solar structures? So first one is wafer preparation. So multicrystalline or monocrystalline silicon wafers are taken using anisotropic etching of KOH and NOH. So texturing is done. So it is dipped and textures of uh, pyramid kind of textures will be formed for light trapping. They are random, not standardized random. Then chemical cleaning to remove all the contaminants, whatever have come from this. Then dopant diffusion. So creating the PN junction with phosphorus diffusion simply. Okay. Then PSG removal. So with phosphorus diffusion, there is a issue that phosphosilicate glass is formed, and that actually makes this to stick. These wafers will stick. So that has to be removed using proper etching processes. It makes it shiny glass like the surface is formed, a thin layer. So that is removed and these will come out, that edge isolation will be there. Then anti-reflective coating and passivation is done. So for this, silicon nitride is used for better efficiency instead of silicon dioxide. Then apply aluminum on the back and screen print front material. So the whole back side is aluminum, and on the front side screen printing is done. So what is screen printing? We will see. Screen printing is simply like a sieve kind of structure which has small holes. So the patterns are open. Whatever pattern we have to make, other parts are covered with, say, a paint that will not allow the material, whatever we have, to go through it. And that is kept over our wafer. A conductive metal paste is taken and it is squeezed. Once, like if you any one of you have seen the process of printing the uh, marriage cards, they are still printed using that the whole structure is uh, the paper is kept over it, a sieve is kept, and over it the ink is put and it is squeezed. Just like that, instead of the ink here, we will have a metallic paste, metal paste that is used to make our contacts. Then heat the cells to alloy contacts and the back surface. So at the same time, front and back both are properly uh, like they will properly diffuse. Then testing and sorting. So quality control for the final module assembly. This reduces the process cost since we have much simpler processes compared to lithography, and here no lithography, no sputtering, uh, no thermal evaporation, nothing. It's very simpler. Okay. Then when texturing in single crystal silicon cells, like the anisotropic etching of 100 surface produces pyramids with 111 facets. In multicrystalline wafers, HNA etch is done. HF, nitric acid and acetic acid. Remember we draw triangle and we saw at different point different kind of optimization is there. That one HNH. This is used to create random texture as there is no uniform orientation. If there was uniform orientation, that that is single crystal silicon. And in case like if we consider in terms of price, single crystal silicon is costlier compared to multi-crystalline wafers. So if if it is available at comparable cost, it's fine. Otherwise, multi-crystalline wafer, if it works the same, uh, there is not much difference. This will be preferred, but it will give random textures as there is no uniform orientation. So after solving the silicon ingots into wafer, the surface is damaged. When we uh, remember the second week, where when we were discussing about the wafer that is taken out from ingot, we clean it everything, and we have silicon ingot that is sawed using diamond cutters, thin thread-like diamond structures that will cut out. But due to this sawing, there is some surface damage. So in this case, KOH serves two purposes. Like in case of silicon wafer for microfabrication or nanofabrication, we have uh, polished surface. But in this case, polishing is not done because the wafer itself is too thin. If it is polished, it will get further thinned and it will break. So it is just cut and brought. And then what happens is that it is dipped in KOH, and KOH serves the purpose of first is it removes the damaged layers, that is the marks, as well as does the texturing. So one one cost cutting is there also, like not cost cutting, that reduces the cost there also. No polishing, nothing, just wafer. It is not shiny. It is just taken, cleaned everything, and then put in KOH. It will remove these like imperfections. Plus, it will make the texturing. So once this texturing has been done, since we are using chemicals like KOH, okay, so that chemical, that is potassium, that can actually contaminate, or any organic or metallic contamination has to be removed. So after this RCA1 and RCA2, what we do for a normal microfabrication process, just yeah, to this same thing are used. So it is cleaned. In case of practical industry adjustment, to reduce cost, some of the manufacturers skip steps or reduce chemical use based on the contamination level, like what kind of contamination is there. Like if it is less, they will just skip, or they will just use a mild kind of chemical. So, and then how this dopant diffusion for PN junction formation is done, how we saw that glass kind of formation is there. Okay, that is done using phosphorus diffusion through POCl3 bubbler. So it is just like oxidation furnace, but uh, POCl3 is bubbled in high temperature furnace. So it can have batches, say 1,000, 2,000 of wafers stacked together. Okay, even say 6,400 wafers in one batch. Okay, and this whole process, phosphosilicate glass forms due to the phosphorus diffusion, and it is removed using the HF etching. So, like after this process, what happens is that phosphorus dope top layer and textured surface. So the surface is textured due to KOH, and now once we do this phosphorus diffusion, it is phosphorus doped. Now, due to this PSG formation, it is it wraps around the wafer, creating a risk of short circuit. So, plasma etching or laser scribing is used to isolate the edge, by removing unwanted phosphorus deposition. This sides have to be scrapped because it becomes thick on the sides. Then silicon nitride Si3N4 is deposited on as an anti-reflective coating. It is not shiny. It is kind of transparent as well as it absorbs the light instead of reflecting. So PECVD is widely used for the ARC deposition due to the cost and throughput. So what are the innovations that have led to advancement in solar cell processing? One is inline wet processing, like wafer pass through bath of conveyor belts for high throughput etching, like PSG removal and cleaning. These are done in batches. They are just passing through uh, bath of these chemicals and they are processed as such. Then high capacity PECVD system. They allow multiple wafers to be coated simultaneously, increasing throughput and reducing cost. And you can understand the advantage of PECVD that nowadays you must have heard that newer iPhones like this iPhone 15, 16, they are having titanium body. So if you check their specification, it is also PECVD coated. It is because it is easier to use this PECVD system compared to sputtering or thermal evaporation method. And to have bulk production and these things, PECVD is a simpler and easier method as well as it can be used for batch processing. Like if we stack together, say 1,000, 2,000 wafers also, we can coat. Okay? So large scale furnaces and equipment innovations like graphite wafer holders in PECVD help achieve 10,000 plus wafers per hour in the present scenario for this solar cells. So continuous improvements are being done to focus on maximizing throughput while maintaining the device performance. Next is screen printing of metal electrodes. So it is basically, as I said, it is having a metal paste, that is viscous metal pastes like silver or aluminum paste for the front and back electrodes. So it is simply a screen or a sieve that can pass through these small particles but not bigger ones, and squeeze, that is a blade kind of structure that is used to drag the metal paste across this, transferring the pattern onto wafer. And this is sorry, this is used to create the electrode pattern. But here one problem is that we cannot go to very lower thicknesses using this method. So a thickness of 30 to 60 micron is possible, and that is fairly good for case of silicon cell solar cells. So along with that, it has the added advantage that it increases the throughput with no need of lithography. So ideally speaking, this also is the starting is of this whole process is kind of lithography only, where this sieve is having first coated with a material that is light sensitive paint. So a liquid that is mixed with sensitizer, then coated. Then over it, whatever structure we have to make. Hello. Yeah, Ajkit, you have
Yes, yes.
some question.
Because
Yeah,
sorry, I'm traveling actually, so I cannot
yeah.
attend very clearly. So
Okay, okay.
if there are any doubts, can you please share your contact number? Like I will
Yeah,
not ask any like not trouble you basically.
yeah, not an issue. I will send over mail. I think I have your mail, right? Yeah,
Okay,
you sent me one mail once. No? I will share over.
okay. Thank you very much, Vikas.
Yeah, yeah,
Thank you.
yeah. Oh, so yeah, so the next one is then what is done next is that over it the pattern is whatever pattern we have to make, that is printed on a paper or a transparent paper, not a transparent, translucent paper, and kept over it, and then this whole structure is exposed to UV light. So just like lithography, the pattern that is made will not be exposed, other parts will be exposed, and then it is washed. And now when it is washed, the area that was not exposed will dissolve in water or whatever is the suitable liquid for that, and then other parts will remain as such, and then for the subsequent processes it is used. So the starting is also like lithography, but it is having a limitation that we cannot go for uh, dimensions smaller than 30 to 60 micron, but it is fairly good for 100 micron, and it is done much cheaply compared to lithography process that includes costly photoresist and other developer and other things, as well as the instrument itself is costlier. But here also alignment marks, everything are used. So now how this back surface field is made. So aluminum paste is printed on the back side. So simply on the back side, using this sieve, aluminum paste is used. So that will make the back contact complete. So this forms a P plus layer, that is back surface field. After firing, that is when we heat it, it makes the P plus layer. Instead of doping it with the P plus or doing an ion implantation will further be costlier. So first is we just do phosphorus. We do the KOH that will remove imperfections and make the pyramid structure. Then we go for phosphorus doping using batch process. Okay. Then we are doing this uh, PSG removal and then silicon nitride coating using PECVD. Then for the electrodes on the front side, uh, we are using silver paste for the electrodes. On the back side, aluminum. And then it is being heated. Once heated, this P plus layer, this aluminum will work as the P plus layer. And since and why on the front silver is used? Because it must penetrate the silicon nitride. So often this happens is due when it is fired, that is, it is heated, it will penetrate through using grit particles. So like it will create uh, like spikes into through the silicon nitride and go to the silicon layer. So a belt furnace, that is these wafers are passing through uh, the furnace using a belt kind of structures, is used for firing, that is hitting the metal paste. So aluminum diffuses to form the P plus layer. Like we have seen earlier also in metallation that aluminum have this tendency of diffusing into the silicon. So here it is being used as the advantage. And the contact solidifies during firing, finalizing the electrode structure. So the present scenario is that it is made using this method. Then testing, sorting, and module assembly is done. That is, each of these wafers are tested. Once tested, they are categorized like high efficiency, normal, low efficiency, and this is important to ensure modules are made from similar efficient cells. Because what if there are, say, array of 100 such cells, solar cells, and in between there are two low efficiency solar cells. So they will reduce the efficiency of the whole solar panel. That's why mostly uh, for high, either like using these low efficiency ones, one low efficiency solar panel can be made. Using high efficiency ones, high efficiency panel can be made. That will be better than having mixing them and then reducing the overall efficiency. Okay. Then module assembly. So tabs connect the sub bus bar. So one cells are made. Then the bus bars of individual cells are connected using tabs to create a series connection. So all these are connected in series. So one module will typically have 60 to 72 cells. One single module or plate or panel, whatever we say, that will have 60 to 72 cells, one panel, and then combining that we can make plates. Okay. So what is the physical structure of this module? It is having a tempered glass on the top to protect the cell from environmental factors. Then encapsulation, EVA, that fills the gap between cell and holds them in the place so that they will not move. And the back seat, that is usually made from TEDLA, that is polyvinyl chloride, or glass in bifacial modules. Sometimes the modules are made such that they are on both sides, front and back. In that case, glass can be used. So the solar module will look like this. On the top, it will be glass. Then EVA films to hold this. EVA film is transparent, so that will hold these cells properly. They cannot move and they will be in their place. And then we have backing protective sheets. To connect each of these modules, such metal ribbons are used for each solar cell, uh, connecting them in series. So see, from the top going to the bottom of the next, then from the top of another going to the bottom of the next. And then we have the junction box that will have the combination of this, and that will have the that will provide the external electrical connections for the module, like taking out the current from there. So in this we have seen about we have like we talked about monocrystalline and multicrystalline modules. Like so monocrystalline module will be of better quality, but it is costlier. Multicrystalline is easier to make, and that is the preferred one. But how to clearly like if you are seeing a solar cell, how will you identify that it is made from a monocrystalline cell or a multicrystalline cell? Because as we saw that while doing the KOH, the anisotropic KOH, the pyramid structure will be random in nature in case of multicrystalline cells. So in case of monocrystalline cell, if you are seeing it, it will you will see a pseudo square shape with rounded corners. So from the top, square structures with rounded corners. So although it's pyramidal in shape, but on top you will see a slightly rounded square structures. Plus, uh, uh, it will be darker and blacker due to more light efficient light trapping and texturing. Whereas in case of multi-crystalline cells, you'll have square-shaped cells that fill more space on the module. So it will be closely spaced because there will be multiple orientation. Plus, there will be bluish tint due to less efficient texture. Since it is not uniform in nature, it will have bluish tint. As well as there will be visible grain boundary from multicrystalline structure, since silicon anyway forms a crystalline structure. So it is not monocrystalline, that the whole wafer is not single crystal, but there will be areas of crystal. So we will be able to see some patches of crystallinity like this. So the structure will clearly be visible that there are some changes. Then there are two other fields that also use similar things that we have, that is photonics and CMOS processes. So in this mostly CMOS compatible fabrication process for silicon photonics is used, and the focus is on silicon on insulator, where silicon is there, on top of it insulator, generally SiO2 is used, and then on top again silicon is used. This is a better and efficient structure, since we have a very thin layer of silicon in which all the processes are happening, and the lower silicon is just a support and nothing else. Okay, so the key concept here is that in active devices are uh, integrated through etching, doping, and metallization. So various functionalities like heater, contacts are made using silicon. So why CMOS for photonics? Like why to go for this CMOS processes for photonics? One is that CMOS processes are standardized and modularized in microelectronics. Okay, as well as it is scalable for large volume fabrication. That's why these processes are now being taken into silicon photonics also. So whatever we have seen now, these processes what we have covered like micro and nano fabrication, they have different fields. Different fields are also adopting these processes because they are standardized, and they have uh, like improved over a period of time, and now they have good throughput. Okay, now we have seen modularization standard. Like for this photonics application, standard flow can be starting with a SOI of wafer, that is silicon over insulator. Make a bottom anti-reflective coating and bake. Then apply photoresist, soft bake and expose for lithography. Then post-exposure bake and development. Then ICP etching, that is inductively coupled plasma for silicon removal. And then photoresist removal to obtain silicon wire structures. So such processes can be used. In photonics, uh, wafer cleaning is also done, but in this case, the contaminants are not ions but particles. Not sorry, are ions and metals, and particles that can cause light absorption and scattering. So, since we are talking about the optical property, they have to be cleaned to have good optical property. Here also, HF, RCA, HF cleaning, RCA cleaning, and Piranha cleaning is used. Along with this, plasma or gas cleaning is also preferred. Wherein, oh, there's a fine. How, what kind of lithography is used in photonics? Again, optical lithography and electron beam lithography, like we have covered. Process steps are also same: photoresist coating, exposure, post-exposure baking, etching, cleaning. So the processes that are in microfabrication, same processes are used even in photonics. In CMOS processing, again, the same thing, that is now from 0.18 micron to 22 nanometer has been reached. So from 180 micron technology, that was the standard some years ago, to 22 nanometer technology has been achieved. Technology nodes, that is using immersion lithography nowadays, 248, 193 and 248 and 193 nanometers are achieved. Key challenges still in CMOS technology, that is proximity effects and resolution effect, and optimization for this, how the etching processes will happen using O2 or hexagonal hydrogen bromide. Okay. It is etching profile and fluid. So when we are talking about uh, this fabrication process integration, there, although whatever integration we do, and the advantage of this integration is that in different fields these processes are these methods are being adopted, but along with this there is always a chance of variability in fabrication. That is, from one batch to another batch there will be some variation. So how to manage the variability in processes, like the effect can be width and height variability on device performance, then spatial and temporal variation in process, like if it is being done here and if it is being done at another place, there can be variation. With time also there can be variation. So the solution is to control non-uniformity at the wafer and the die level itself, instead of controlling the overall variability of the whole fabrication process. So that has to be controlled on the wafer and the die level itself. And if it is controlled at this level, overall fabrication process will have the uh, less variability. Then uh, cladding and planarization is another thing. That is, silicon dioxide is mostly used for cladding in photonics devices like PECVD, LPCVD, and HDP is used for the silicon oxide deposition, and planarization again using chemical mechanical polishing that we covered in the previous class. So uh, if the surface is smooth and flat, then only it will have the optimal device performance, like reflection, adsorption, whatever we are planning for. Having rough surfaces will have different angles, and that will lead to differences in our optical properties. So after this, we have some questions related to different the topics covered. That is, which of the following is correct? Gowning is necessary while entering a clean room to protect the person user from contamination inside the clean room. Personal protective gear is necessary while handling chemicals and processing a device. The dust or particles present in the atmosphere do not affect device performance, or all of the above. Any answers? Yes. So first is incorrect because gowning is not to protect us, like the user, but it is to protect the clean room environment. That is, the devices should not get contaminated from us or the user. Okay. Whereas to protect the person while handling chemicals, proper PPE kit, personal protective equipments have to be used for safety. Yeah. The third statement is also incorrect because atmospheric dust and particle can severely affect the performance of sensitive devices like semiconductor. Okay. Now the next problem. Select the correct statement. New wafer do not require a cleaning step in device processing. A material deposition is always the first step for processing a cantilever. Remember the cantilever of silicon nitride that was deposited and then released by removing the layer below. And wafer cleaning is mandatory before deposition or lithography processes. So the correct answer is option C. Since we don't want any contamination on the wafer surface. A is incorrect because even if it is new, it has to be the wafer has to clean to remove the native oxide and organic residues or other contamination. And it is not necessary to start with a material deposition. Sometimes lithography is done first, like we saw lift-off method. So in that case, lithography can be done first, then followed by material deposition. So it is not always the first step. Now, there is one problem where a device engineer wants to fabricate a device with a width of zero point 0.5 micron and a height of 2 micron. So having a aspect ratio of 0.5 to 2 micron like this. Okay. What kind of etch process should be selected? Isotropic dry etching, anisotropic dry etching, isotropic wet etching, or anisotropic wet etching? Any answers? It's anisotropic dry etching because for high aspect ratio structure, since the difference is too high, uh, like 1 is to 4, okay? As well as the angle that we see here, that is not the standard angle between 111 and 100 plane. So we cannot go for uh, wet etching, and that's why anisotropic dry etching should be preferred in this case. Next is in a lithography process, moisture bake reduces the contamination on top of wafer. The thickness of deposited film cannot be measured using a step height measurement technique without patterning, and an isotropic etch process can achieve a cantilever release process. So first one is like moisture baking, that is done to reduce not the contamination but to uh, the name itself suggests that to remove the moisture and like to dry the photoresist. In case of measuring step height, that is generally profilometer, it can work only when there is a difference. It cannot measure the thickness over a film. There are techniques like lipsometry which can do, but they are limited to certain uh, materials only, uh, which are generally transparent in nature. and have well-known refractive index. But what about opaque materials? For that, we have to create pattern. So this one will be correct, this one will be wrong. And it's not necessary to have an anisotropic etch process to achieve cantilever release process. So conformal deposition, that is uniform deposition with a low deposition rate, that is 1 atomic layer per minute on dense or too closely spaced structure, will result in a void. Is it true or false? It is false because, yeah, okay. It's false because conformal deposition with low deposition rate, that is like we saw the ALD method, atomic layer deposition, is typically achieved uh, through ALD. So it can deposit thin film layer by layer with high precision. So it will have uh, excellent coverage, as well as it is the first word itself, that is conformal. Conformal means it will cover the maximum area. It will have very good coverage. So even for high aspect ratio structures, it will cover the whole area. So there is less chance of a void. If it was for a normal deposition, like in case of say sputtering, it could have resulted in void. But if we are talking about 1 atomic layer per minute, like ALD, such methods will give us no void and it will have a conformal deposition. So now, one problem is that suppose you are an enthusiastic entrepreneur trying to develop micro needles to have a painless drug delivery tool. That is, you are trying a rudimentary prototype like hollow needles using two lithography masks. So to define the pins, like hollow cylinders, these are the pins. Okay, so one structure like it is needle kind of structure, and in between there is a hole, a tube kind of structure. Okay, so you are using two masks for this. As this process has two lithography steps, you need to align one pattern with another accurately. So alignment accuracy depends on how rigidly you hold the substrate under the mask. If you use a vacuum chuck to hold the substrate, so in what order will you pattern the substrate for better alignment? First, create the pin, that is the hollow cylinder. Turn the substrate upside down like this, and then uh, do the next step, that is create the through hole, that is uh, going from top to bottom, or make the through hole first, the whole pattern like this, and uh, then do the second patterning, that is making the needle. So
Second one.
second one, and why? Because if you see the structure, it is vacuum chucked, and if these needles are just hanging over it, it will not be able to hold the wafer properly. So to hold the wafer properly, a flat surface will be preferred, and that's why the second method is better in this case. If a solar cell manufacturing company makes a module in 2 minutes and each module consists of 60 cell wafers, keeping throughput in mind, which of the following process can be accommodated in the production line? Spin coating dopant surface, that takes 10 seconds per wafer, where each wafer is processed one after another. it is a sequential process. Second is dopant diffusion, which is rapid thermal processing, that is heating at a certain temperature and then just leaving, which is taking 100 seconds per batch, but each batch is of 60 wafers. Back surface aluminum electrode deposition by sputtering, that is taking 5 minutes per batch, and each batch is 60 wafers. Silicon nitride deposition by PECVD method, that is taking 10 seconds per batch, and each batch is having 4 wafers. So which of this process can be accommodated in the production line? Yes, any answers?
Each batch with 60 wafers.
Yeah, so B and C both are having 60 wafer batches. Certainly having batch will have an advantage over the sequential process like one, or having 4 wafers in both the compared to both the processes. We have advantage of having 60 wafers in a batch. But among these, which one will be better? 100 second per batch or 5 minutes per batch?
5 minutes per batch.
That will be slower. We want faster. So,
Yes.
yeah, so that will be 100 second per batch. Since we want to increase the throughput, that will be to make it faster, we can go introduce this dopant diffusion, that is having 100 second per batch and processing 60 wafers in a batch. In a design flow, a lithography rule check is done after mask preparation. Is it true or false? What are the rules that we have to check after? Yeah. So once, if it is checked, once the whole uh, mask has been made, then we'll have to, if there is an error, we will have to check we will have to make the mask again. So in case of a design flow where design is taking care of like understanding the process is understood before making the design, in that case, this lithography rule check is done before the mask preparation, not after the mask preparation. And that ensures that the mask that we are making don't have to be remade. So, for screen printed solar cell fabrication, what is the correct process flow? So as we have seen, the first thing that is done is texturing. So here itself, the first thing will be texturing. Then either, yeah, only one option with that. Then cleaning, dopant diffusion, PSG removal, edge isolation, then followed by screen printing the electrodes and RTA. So I think, yeah, this one. And then this will be followed by, actually it will be followed by this D, that is front edge printing, rear aluminum or edge screen printing. Then no edge isolation, no PSG removal. And then it will be RTA and then other metallization process for the connections. So that's all. So this is the end of the course, this 12 weeks course. Any questions till here?
No, thank you, sir. No questions because I did not hear actually. To be honest, I was traveling, but I
Okay.
will go through the recording and we'll get back to you.
Yeah, sure. Not an issue. Yeah. Okay, so that's all. Best of luck to everyone. Thank you.
Thank you very much, Vikas.
Okay.